Welcome to the Real News Network. I'm Paul Jay in Baltimore. A few days ago, we ran a couple of interviews with climate scientists. And in those interviews, we promised that you, our viewers, could ask you questions and challenge those scientists. And this is the beginning of a series where they will attempt to answer your questions. We're also in the midst of our spring-summer fundraising campaign. So in case you haven't noticed, we have a $50,000 challenge grant. Every dollar you give triggers another dollar. And if you want us to keep doing real news programming, as you know, because you've heard me pitch this more than once, we need you to support us. We don't accept government funding. We don't accept corporate underwriting. We don't sell advertising, which means it's all about viewer support. So there's a donate button over here. If you click on it, it will help make sure we're still here over the summer and heading into the U.S. elections. Now, with no further ado, we will invite our scientists to join us and we will start asking your questions. Now joining us from Paris is Valérie Masson-Delmotte. She's a French paleoclimatologist. She holds an engineering degree from l'École Centrale Paris in physics and fluid transfer. Since 1997, she's been a senior scientist at the French Nuclear Energy Commission. She served on numerous national and international projects, including the Intergovernmental Panel on Climate Change. Thanks for joining us, Valérie.
Hi.
And also joining us, Jeff Keel's a senior scientist at the National Center for Atmospheric Research, where he heads the Climate Change Research Section. He's published over 100 articles on the effects of greenhouse gases on the Earth's climate, the effects of stratospheric ozone depletion on climate, and the effects of aerosols on the climate system. He's also the co-author of Frontiers of Climate Modeling. Thanks for joining us, Jeff.
Thank you.
So here's how this format's going to work. We're going to ask one, maybe two questions per segment. We want to give our scientists time to dig into these issues. And we will do multiple segments. So over the course of the next week or two during the fundraising campaign, we will be running more or less daily as we work our way through questions. And we will do it again. Once you viewers have seen this series, I'm guessing you're going to have more questions, more challenges, and then we'll do it again. And we'll keep doing it until we think we've kind of really dug into all these issues. Now, this part of this section is really about the science. Some of the questions we received were a little more political and had to do with, what are the real solutions and how are people going to pressure governments like the American and Canadian government that aren't doing much of anything. We're not going to deal with that now. We're going to stick to science, and we may even find our scientists may, in response to a certain question, may say that's not their expertise, which is fair enough, because this is about science. And if we do hit a question like that, then we will go find a scientist with that expertise, and we'll deal with the question then. So here we go. We're going to start, and I'm going to read these off my device here. So here's the first question. I'm sorry. My first question, I'm on an electronic thing and it just moved. Okay, here we go. The evidence does show a relationship between the rise in temperature and the rise in CO2. What it does not show is a cause and effect scenario that definitively proves that the temperature rises because of the rise of CO2. The viewer writes, I know there's a great temptation to jump the gun since the evidence shows a relationship, but that is, again, bad science. And this is coming from, he identifies himself as WWVND, and he put this question up on YouTube. Okay, Valérie, you want to take the first shot at an answer?
Okay, so the question is about what is observed with regards to the timing of temperature changes and CO2 changes, and also about the methods that are used to relate this type of observations with causality. And there are a number of answers that could be brought in, depending on the time scales that are considered. One could look at the last centuries, one could look at glacial interglacial cycles, or at geological past. My own expertise is focused on glacial interglacial cycles, and most of you have already seen these curves showing a tight correlation between Antarctic temperature and atmospheric composition, CO2 concentration, methane concentration, that is measured in Antarctic ice cores. And so this correlation is quite striking over the last 800,000 years. But if you look in detail, what you observe is that at the start of an ice age, Antarctic temperature is falling down before CO2 is going downwards. And if you look at the shift from a glacial period to a warm phase, at the moment, we also think that there is a lag for some of the time periods between the rise in Antarctic temperature and the rise in CO2. What's important to consider on this time scale is what is the driver and what are the feedbacks. And the driver of glacial interglacial climate changes, there's no doubt it lies in the incoming insolation that is distributed at the Earth's surface. And this distribution depends on the orbit of the Earth around the Sun. So there are regular shifts in this orbit at timescales of 20,000 years, 40,000 years, 100,000 years. This changes the distribution of insolation, and that's the main driver of glacial interglacial changes. It acts on ice sheets and it acts on climate. And when climate is changing, especially ocean circulation is changing, then it controls, it regulates the amount of CO2 that is transferred from the deep ocean to the atmosphere. So on this time scale, CO2 is both a feedback to the impact of orbital forcing on climate, but it also acts on climate. And there is no doubt that when you add CO2 in the atmosphere, you alter the radiative properties of the atmosphere, and it has an effect on climate. So in order to understand the exact role of CO2, you cannot just rely on data. You need also to model the processes at play. So we use basically the same climate models that are used for present day for future projections, and we make tests with these models. What if you have constant CO2? What if we prescribe to these models the glacial interglacial changes in CO2? And basically the answer is you cannot explain ice ages with a constant glacial CO2. It doesn't work. In order to explain quantitatively, but also the spatial patterns of glacial interglacial changes, you need to take into account the effect of CO2. And the way climate models account for this effect seems correct at first order compared to their performance for glacial climate. So there's an ongoing effort, in fact, in using data from glacial climate to test the realism of the sensitivity, that is the response of climate to CO2, that is a result of numerous feedbacks simulated by climate models.
Okay, Jeff, do you want to add something? And let me say that we've got a couple of questions I won't read, but they're similar, which is that CO2 is a naturally produced thing. That algae produces CO2. There's all kinds of natural ways the Earth produces CO2. And there's nothing wrong with CO2, and that nature has a way of dealing with CO2. So maybe you can deal with that. Plus, do you want to add anything to what Valerie said?
So let me actually just start with the question you just posed about the natural sources of carbon dioxide. Indeed, there are natural sources of carbon dioxide, and those processes or sources put enough carbon dioxide in the atmosphere that it's actually very good that we have that carbon dioxide in the atmosphere, because left to its own, the natural processes supply enough carbon dioxide to the atmosphere that it keeps the planet's Earth surface warm enough for life to exist on Earth. So this is actually the positive aspect of the greenhouse effect, that if we took all of the carbon dioxide out of the atmosphere that nature puts in without humans changing it, well, if we took all of it out, you can actually do a fairly simple calculation to show that the temperature of the Earth would drop a tremendous amount. And what also operates is that as you start to drop the temperature by taking carbon dioxide out completely, the amount of water vapor also decreases in the atmosphere, and that cools the planet even more. So there have been some nice studies showing that carbon dioxide at its pre-industrial levels is absolutely essential for life on Earth. Now, the problem is we humans are actually going in and changing the amount of carbon dioxide at a fairly substantial magnitude. For example, one natural source of carbon dioxide is volcanic activity. Volcanoes, and you can think, most people think of volcanoes as explosive, but there are lots of volcanoes that aren't exploding around the Earth, but they're still leaking out carbon dioxide. So you can measure how much carbon dioxide is coming out of volcanoes, and people have done this, and they've compared how much volcanoes are putting into the atmosphere compared to humans. And it turns out that humans are putting hundreds of times more carbon dioxide into the atmosphere every year compared to what volcanoes are doing. In fact, a recent calculation shows that within a period of 3 to 5 days, humans put more carbon dioxide in the atmosphere, more carbon dioxide in the atmosphere than volcanoes do in a whole year. So there's, yes, nature does put carbon dioxide in the atmosphere, but when you actually add up the numbers and look at the hard facts, it's clear that humans are outstripping nature now by orders of magnitude, factors of tens.
I mean, one of the viewers wrote in as sort of an argument in support of what you're saying, that nature produces CO2 and nature has ways of reducing CO2.
Yeah.
Humans are adding to CO2 without reducing it.
Right.
Is that a correct way to state it?
Yes. Essentially, nature also has, if we weren't on this planet, and we weren't, at one point in Earth's history, the atmospheric carbon dioxide amount is basically regulated by how much is put into the atmosphere through volcanic activity and how much is taken out either in plants on land or organisms in the ocean, so-called ocean sink of carbon dioxide. And in the grand long time scale of things, tens of hundreds of millions of years, because these processes work very, very slowly, that determines how much carbon dioxide is in the atmosphere. And it reaches a balance unless, say, volcanic activity increases over a certain long period of time. And then what happens is carbon dioxide in the atmosphere increases. And guess what? We actually have examples of this in Earth's deep past. We're talking tens to hundreds of millions of years ago. And what we see is that when carbon dioxide was high in those past periods, the planet was much warmer. It was so warm 30 million years ago that there was no ice on either Antarctica or Greenland. It was significantly warmer than it is today. And the amount of carbon dioxide in the atmosphere then was about 3 to 4 times what it is today.
Well,
so
we actually, let me just ask you, we had a question related to that specifically. This is a question from, he calls himself Silo Cyber Spaceman.
Okay.
We got to get people to use their real names here. But he asked a question that if 80 million years ago there was no ice on either of the poles, how are temperature and carbon levels determined from that time period?
Well, we have other ways of doing that. There are deep sediment cores in the ocean. People go out and very brave people go out on boats in the middle of the ocean and they drop cores down into the sediments at the bottom of the ocean. And those sediments can take our climate record back 100 million years, roughly. And so by using those, there's geologic, geochemical information in those sediment cores that tells us about what the planet was like past the ice core record. And then if you go back even further, because the sediments at the bottom of the ocean can only take you back about 100 million years or so, If you want to go back further, then you have to go to the geologic record, the rock record. And there you go out to the different places around the planet where you can date the geologic rocks and look at the formations of the rocks and the geochemistry of the rocks. And that, again, tells you something about what Earth's climate was like even further back in time. So we have this array of techniques. The ice core records will go back about 1 million years, and then beyond 1 million years, you use the sediment cores from the deeper parts of the ocean. And then if you want to go back even further than that, you use the Earth's geologic record.
Right. Okay, we're going to wrap up this segment. But if you want to respond or ask a question about this segment, please identify it in your email or in the comment section between the video, so we can tie your comment to the specific segment, and then we can explore this issue even further. So don't forget, this is all part of our matching fundraising campaign, and if you donate $1, we trigger another $1. So please donate generously and join us for the next segment of our further discussion on climate change science on the Real News Network.